Hi, and welcome to today's ACM Learning webinar. This webcast reflects ACM's deep commitment to lifelong learning with a goal of empowering computing professionals and students who join ACM's worldwide community of over 100,000 members. My name is John West. I'm the director of the DoD High Performance Computing Modernization Program, and I'm a leader in the ACM Special Interest Group on High Performance Computing, an affiliation I share with today's presenter, Bill Gropp. If you aren't yet a member of SIG-HPC, I encourage you to find out more at sighpc.org. So before we get started, just a few housekeeping issues. ACM offers educational and professional development resources that help members improve their skill sets and enhance career development. Our members are able to stay competitive in the fast-paced computing world with a range of ACM Learning Center online resources at learning.acm.org. You can see some of the highlights of these offerings on your screen now. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. Together with timely computing information published by ACM, access to the ACM Digital Library, and international conferences, ACM enables its members to solve critical problems using new technology that enriches all of our lives. Just a few more housekeeping items. In the top right-hand corner of the slide area on your screen, there's a button that will allow you to enlarge the slides. You can do that at any time, also by dragging the corner of the slide window. Your slides will advance automatically throughout the event. You can minimize the slide area, the Q&A, and bio screens using the buttons on the bottom panel. You can also use a number of widgets also found on the bottom panel, including Facebook, Twitter, a sharing tool, and a resource list where you can get a copy of the slides. If you have any problems with the program during the presentation today, please press the F5 key if you're on Windows or Command-R if you're on a Mac, and that'll refresh your console. You can also close or relaunch the presentation if you're still having trouble. If you continue to have problems, take a look at the webcast help guide by clicking on the Help widget below the slide window. To control the volume, adjust the master volume on your computer. At the end of the presentation, you'll see a survey URL on the final slide. We'd love it if you'd take a minute to fill that out to help us improve our next webinar experience. This session is being recorded and will be archived if you have friends or colleagues that can't make it today. Everyone who's registered will receive an automatic email notification when it's available, or you can check learning.acm.org in a few days for updates. At the end of the presentation, we will have time for questions, and we hope you have lots of great questions. If you think of something during the presentation, please type it into the Q&A box and click on the Submit button. You don't need to wait until the end of the presentation to begin submitting questions. You may also use the Q&A box and the survey at the end to suggest topics for future webinars that might be of interest to you. So during the presentation, you can also use the Facebook and Twitter widgets at the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag #ACMWebinarGropp. We'll be watching for your tweets. So today's presentation is Changing How Programmers Think About Parallel Programming, presented by Bill Gropp. Bill is the Thomas M. Siebel Chair in the Department of Computer Science, the Deputy Director for Research for the Institute of Advanced Computing Applications and Technologies, and the Director of the Parallel Computing Institute, all at the University of Illinois in Urbana-Champaign. He received his PhD in computer science from Stanford University in 1982. He was on the faculty of the CS Department at Yale from 82 to 90, and a member of the Mathematics and Computer Science Division at Argonne National Laboratory from 1990 to 2007. Bill's research interests are in parallel computing, software for scientific computing, and numerical methods for partial differential equations. Bill is a fellow of the ACM, the IEEE, and SIAM, and is a member of the National Academy of Engineering. So now, Bill, I'll turn it over to you.
Thanks, John. I'd like to thank the audience for joining me when I talk about something that is maybe a little different than just how do we program a parallel machine, but how do we think about it? How do we organize our thoughts? How do we plan? How do we design? And so you'll see on the outline that I'm going to talk a little bit about how we think about it, a common approach to building parallel programs, particularly in the scientific and technical computing area, which is called bulk synchronous parallelism and bulk synchronous programming, and things that we need to start thinking about, particularly as we consider applying parallelism to very, very large machines. So that's what we're going to be covering today. One of the first things to remember when we're talking about parallel programming is, why do we do it? Now, I suppose that some of us do it because it's fun and challenging, but most people do it because they have no choice. They need to get more computing resources than they can get from one core or one computer. And so the focus is almost always on performance. And that has traditionally been in terms of the compute performance, but it might be other sorts of things that you're looking at. For example, disk systems often use parallelism to get more bandwidth performance. And you may also use parallelism to get more reliability in the presence of faults. And high-performance computing is really just that. This is ways to get exceptional performance from computers at all scales. So I include in high-performance computing, something which is the subject of our special interest group, is getting exceptional performance even from a single core, which is, of course, an important part of getting exceptional performance from a full parallel machine. So to start with, will help me if the audience can let me know what they use for parallel programming. If what you use is not on this list, I will deduce that by subtracting the number of votes from the total number of attendees. So if you just take a minute or so and look at this poll and see how much you use. And I see you're getting a lot of good votes right away. Give you another minute, see if anybody else wants to respond. Okay. Okay, so this is a very interesting set of results. I see a lot of you are pthreads users, as well as MPI and OpenMP. In fact, it's interesting that there's a fairly uniform distribution across some of the major choices. So I think that that's good. I think that means that you are listening to the right presentation. So when we think about parallel programming, there are, of course, many, many ways to do this. One easy way to break it down is into whether it is coarse-grained in terms of big tasks that are coordinated, or fine-grained, where you effectively divide a single task up into many different operations that can be done. And sometimes these are called task parallelism for the coarse grain and data parallelism for the fine grain. So as an example of coarse-grained, thinking as an academic at a university, setting a bunch of students on different problems in a related research area, so as to put together a research program with a related theme, that's a sort of coarse grain or task parallelism. Or I could look at mailing lots of letters and then give different people the lists, and they would manage all of the tasks for that. And there are a lot of tools to help with this. Threads, of course, is a natural way to do this. People have done this sort of parallelism by using fork or create process. There are also tools that help you manage task parallelism. An example of a fine-grained one is, we can look again at that list of letters. If I broke that down into a series of steps and then had everybody execute their step in sequence, that would be much more fine-grained. So for example, we'll sit everybody down, have them write out the letters, Then when they're done with that, have them stuff the envelope. And then when they're done with that, write the address and so forth. And there are a lot of common tools for that as well. So a common use of OpenMP, for example, is for this kind of data parallelism. Vectorization, whether it's the old, much older vectorization that some of us may remember from machines like the original Crays, or vectorization for the modern commodity microprocessors where the vectors are much shorter, that's an example of fine-grained parallelism. And both of these are relatively easy to think about. It doesn't mean that you don't make errors, but they're relatively easy to think about. Now, let me look at one example that I'm going to use to start setting the discussion for how some of the ways of thinking about parallelism may lead us down the wrong path. And so a common example that is used in scientific computing is to do a computation on a mesh. This mesh is a way to approximate the solution of a differential equation over a domain. What I've shown here is a two-dimensional domain. So, for example, if I'm trying to compute the deflection of a drum head, in this case a square drum head, I might set up something like this. And when I'm applying my equation, I will need to look at values that are nearby, and I've just put up a little red plus. This is called the stencil that indicates when I'm doing my computation, I need the data at the center of that plus and data from just the neighboring points. In a sequential code, this is very easy to write. I would use a for loop in C or a do loop in Fortran to write this out. Now, if I want to parallelize it, there are a lot of obvious ways to do it, and one of the things that you'll often see in a book on parallel computing is to do a domain decomposition, which I've illustrated here, where I've divided that domain, that grid, into 9 pieces for 9 processors, and I can put my stencil on that, and then I will do my computation. And that gives me a reasonable way to build a parallel program for this problem, and it's one that is in very common use today in lots of applications that are looking at solving these differential equations. Okay. Now, of course, it's a little more complicated than I've just described. So when I divide my domain up into these pieces, it's sort of okay when the stencil lies in the middle of a piece. But what happens when the stencil lies at the edge? It means it needs to reference some data that is on a different process. And to do this, I'm going to have to acquire that data somehow. And when we're looking at building a parallel program, I need to ensure that I can access that data. Now, I'm not going to talk too much about the details of this, but I'm assuming here sort of classic, what's called a distributed memory parallel computer. That's where there is no direct access to data that's being managed by another processor. In a shared memory system, there is a way to get that direct access, but there are other issues that need to be taken into account. So in the case of a distributed memory system, where I need to get access to data that I don't have, what do? Well, what we classically do is make a copy of it. So if we look at this next slide, what I've done is I've taken those original domains and I've added these yellow squares around them. That's extra space in which I'm going to make a copy of data from one of the neighboring processes. So those of you that are MPI programmers are undoubtedly familiar with this. Those of you that are OpenMP or pthread programmers, you may also be familiar with this if you've ever made a local copy, thread private copy of data in order to ensure that you get better performance in accessing that data. So all we're doing is arranging to make a copy of data that we're going to need in order to get efficient execution of our application. And so now that stencil that was at the edge now references a point that's in this copy area. And so all that's left to do is to arrange to get that data. And so what we typically do, for example, in an MPI program, is we have each process determine what data its neighbors need, and that I've outlined in green here, and have it send that data to the neighbors. And there are many ways to do that send. I'll say a little bit about what those might be a little later. But in the classic message passing or communicating process model, that each process would send to its neighbors data, and those neighbors would actively receive it. So in this image, you see that process has sent the data that each of its neighbors need, and it goes from the data owned by that process into the copy areas for the neighboring processes. Okay, so this is fairly straightforward, and if I write this in pseudocode using, I'm going to use MPI as the message passing interface, it has two obvious steps. There's a exchange of the halo data. So this is the transfer of data that we just saw on that previous slide. And that might be implemented, for those of you who know MPI, with, say, MPI I send, MPI I receive, and await all, or maybe with MPI one-sided operations, so MPI put and fence, or even some of the new collectives like MPI neighbor all to all. And then there are a bunch of other possibilities here. Once I've exchanged that data, I can easily run the code that does the computation. And so I do that for stencil computation on the local memory, which includes both the data owned by this process and the data that was given in that copy. Okay? And so I have these two phases. It's a very simple way to think about the code. I can think about correctness. Do I have the data transfer part, the exchange halo part correct, and then do I have the perform stencil computation part correct? And so this is where we have to start thinking about the parallelism. And I want to say right off the bat that parallelism is hard. Don't let anybody tell you otherwise. And one of the reasons it's hard is that not only do you have to get the right answer, but you have to get it fast. And in many cases, particularly with modern computers, fast is very difficult. In some ways, it's harder than correctness. And again, if you're using parallelism, you're trying to get more performance usually than you were able to get without parallelism. So getting the right answer and getting it fast is one of those things that's very difficult, and it's like that old joke about you can have it fast, correct, or on time, pick at most two. And so parallelism is definitely like that. And correctness also requires an understanding of how the different parts of a parallel program interact. And people are notoriously bad at this. It's much easier for people to debug straight-line code than to debug parallel code. And I will speak from personal experience. I'm working with some colleagues. We published an algorithm, a parallel algorithm, and it's a clever parallel algorithm, and it turned out to be almost correct. And finding that correctness was done only by another group who had a program that analyzed parallel code in excruciating detail, and they discovered a very subtle flaw. It made me a believer in formal methods applied to parallel computing, and also as a reminder, just again, of how difficult this is. And we all really know this because much as we might complain about our management, organizations have multiple layers of management because it's very hard to organize and manage concurrent activities. So as we're thinking about parallelism, we need ways that allow us to understand correctness and performance at the same time. And a common approach that is used, particularly in high-performance computing, is something called bulk synchronous programming. And I want to be very careful with the terms here because we're also going to talk about bulk synchronous parallelism in a few slides, and they're slightly different. So in high-performance computing, this refers to a style of programming like we've just illustrated, where the computation alternates between communication and computation phases. And in this PDE simulation, we had this communication phase, a local computation phase, and then another thing which I didn't talk about in the initial example of that slide. If I'm doing one of these differential equation simulations, at some point I need to check how accurate it is my answer converged, and so forth. And that's a kind of communication and computation that requires getting a result from everybody and checking it. So, for example, I might ask, did every process compute a number that was smaller than a certain threshold? And I need to know if they all do. Okay, so this is a widely used approach. An awful lot of applications use this on the very large system that the National Science Foundation has provided for its users that is installed at Illinois. Quite a few of the application groups who are running very challenging problems have organized their code in this way. And there, again, are really good reasons for this. It fits the way you might want to look at the application. These communication phases and computation phases were a clear fit to sort of a natural way of thinking about that differential equation simulation. When you're doing I/O, when you're writing out a result, a natural way to look at it is I compute the result and then I write it out. What else would I do? A checkpoint, which is a way to recover, restart a computation after a failure, again, it's very easy to think of it in terms of I let my entire computation go to a point where it's easy to understand the state, and then I will write that out. And so that's a very nice way to look at it. Now, there's a related model called bulk synchronous parallelism, which is was a way that was proposed to think about both the performance and the correctness of a parallel program all at the same time. And this is a very important approach. It's been around for a long time. If you want to read essentially the original article, you'll find it in the Communications of the ACM from August of 1990 by Leslie Valiant. And it's a classic approach to solving the hard problem of correctly programming, correctly writing a parallel program and getting good performance. So you break it down into steps that you can reason and think about. And this is similar to the bulk synchronous programming that I talked about. There are a few differences, one being that many practitioners of bulk synchronous programming don't consider the performance as much a first-class part of the model as it is for bulk synchronous parallelism. So you might have thought at that point that I was going to explain why bulk synchronous parallelism and bulk synchronous programming was exactly the right way to start thinking about parallelism. And instead, I'm going to tell you why it's no longer a good way by itself to think about parallelism. And why is that? Why is it bad? Well, it has a lot of limitations because it has a lot of implicit assumptions. So, for example, if we go back to that example where I divided the mesh among my processors, there was an implicit assumption there that by evenly dividing up the mesh, the number of points that I was working on, I had evenly divided up the computational time, even more so than the computational work. And that's just not reasonable anymore. In many ways, it never was too reasonable. After all, think about how easy it is for you to try to predict how long your code is going to run to great accuracy. So, for example, just try to predict how fast even a dense matrix multiply is going to run. You know how fast it should run, but if you write down some code and give it to a compiler and then measure it, are you going to be within a factor of 2? You'll be doing well in many cases if you are. And this applies to all parts of the system, and we're seeing that our computers are becoming more and more complex. Many constraints are driving the design of computer hardware to contain more specialized pieces, and those will make it increasingly difficult to predict performance. There are all sorts of things that make it hard to predict performance. Now, before I go on, another question that will help me understand where the audience is. I'd like you to quickly answer this quiz about how many cores do you think a large system will have in 2 years, in 2015? And if you think that the number is under 500,000, select the 500,000. So I'll give you just a couple of minutes to look at that. For those of you who wonder what I'm doing, is I'm using the popcorn rule here. I'm waiting to see when votes start to trickle in the way popcorn starts popping at the end of the bag. Okay, I think we're about there. There we go. Okay, so here's what the audience thinks, that the large systems will be, again, it's sort of evenly divided here. 500,000 or fewer, about a quarter million, about a quarter, 5 million, about a quarter, more than that, about a fifth. So some of you will be surprised to note that large systems today are over 1 million cores. And in a couple of years, I will expect them to be at least 5 million. And in a core here, I'm using a sort of full-fledged processor core. If I was counting up individual GPU cores, depending on how I defined a core, we could be well over 5 million in 2 years. So why is this important? Why do we go through this? Well, in all of these bulk synchronous models, there's that synchronous term. And as systems get really large, this synchronous term starts causing real problems. So if I've got, say, 25,000 or 100,000 nodes, each with many, many cores on a node, just getting all of these nodes to agree that they've reached the same spot in the code, which is effectively exchanging one bit of information, the I am here bit, that can take, if you're lucky, at least 10 microseconds, or say 20,000 cycles per core. So just imagine the amount of work that you can do if you spent 20,000 cycles on each of 1 million cores. So that synchronous part starts becoming a real problem. In a lot of these calculations, we have things that are called barriers or synchronizing communications. So a barrier is pretty simple. The definition of a barrier is it's a step where every thread or process has to enter the barrier before any of them can exit. There are all sorts of ways to implement this, both in hardware and software. Some of the high-end parallel computing systems, in fact, made extensive use of specialized hardware to get very fast barriers. You can also do this by exchanging messages. So there are some fairly straightforward algorithms that take log p time. So if you have p processes or p threads that you need to agree on a barrier, you can do that in log p time. Of course, note that if you've got 1 million cores, log base 2 of 10 to the 6 is already 20, and a communication step can take a microsecond or more. That's one of the reasons why I said that the barriers are already that expensive. Now, I do want to note that barriers themselves are rarely required in applications. You may see them a lot, and there is a delightful little paper that's on this link that talks about a tool that identifies barriers that are functionally irrelevant, ones that don't change the semantics of the code, but they might slow it down. What are more interesting are communications that are synchronizing, that they have the same property that no one can exit the operation until everyone has entered, but that they do a little more computation. So a simple example of this is a test that all processes have computed a value that's less than a certain threshold. And so if you want to know whether that's true for all, then obviously you have to wait until everyone has contributed their yes or no bit to that, and then you have to combine them to see what the result is. Another example that's very important in technical computations is a dot product, where you have a vector distributed across a machine. That vector, for example, might be that mesh, and I may have 2 meshes, or I might have that mesh and I want to take the norm of the values. All of those things will create a synchronizing step in the computation. Okay, so that's maybe a little unfortunate, but why is that bad? Well, as we look at these applications, we look at the style of parallel computing that is built around having a communication phase and a computation phase. We find that we have lots of synchronizations in the communication. It might be similar to the barrier synchronization, the very strong synchronization, but it may also be a little weaker. So the halo exchange that we saw also synchronizes the processes. It just does it a little more weakly. So no process can continue until it has exchanged data with its neighbors. But for all the processes to continue, all of the processes will have had to have exchanged data with their neighbors. So it's possible that one process may be able to get going a little earlier, but at some point, the fact that everyone has to do these exchanges for the computation to proceed also provides a sort of synchronization. I should mention here, and this is a sort of a foreshadowing of things to come, is some programming implementation, some ways of writing code, some programming languages or models may synchronize more strongly than required in the algorithm. In other words, the way that you might naturally express an algorithm in a certain style of coding might create more synchronization requirements than the original algorithm. So for example, I mentioned using MPI put and MPI fence for this halo exchange. That's a way where each process directly writes the data that its neighbors need, but the MPI fence makes sure that those have all completed, and it makes sure that they've all completed across all of the processes, not just the neighbors. And so that style would change a weakly synchronizing step into a strongly synchronizing step. Okay, so why does that get bad? Well, what if one core out of those million cores, just one, is late for any reason? It might be late because that core was preempted by the runtime system to help with a retransmission of a message. It might be late because the computation on that part of the mesh had a lot of very small numbers and caused what are called gradual underflows in the IEEE arithmetic, which are not handled as fast in the hardware as the other floating point computations. I could go on and on about why I might find that one of these cores is slow. And so what that means is that the apparent time for the communication step changes from, you'll see that actual time for communication on this figure, it changes from that really small value to this apparent time, because all the other cores end up waiting because of the synchronizing communication. So by structuring the code to have these synchronizing steps, it means that you have become sensitive to anything that delays any of those cores. And it can get worse, because what happens if while one of those other cores are waiting, yet another one is delayed? What you can find is that this can cascade. There was a nice paper illustrating this at the supercomputing conference at SC10. In fact, it won the Best Paper Award. And you can also find this in the ACM Digital Library. And it shows that if you have an occasional delay sort of randomly across occasional processes, your system gets big enough, these delays can cascade so that you can suddenly lose literally orders of magnitude in performance. And this is a function of scale. As the system gets bigger and bigger, the likelihood that you'll get a delay while you are delayed becomes effectively 1. And that means that applications that were effective in parallel suddenly become ineffective. And there really are many sources of delays. Many of you may use the approach of dedicating a core to, for example, the operating system. And that is helpful. It does remove one of the sources of delays. Unfortunately, it doesn't remove them all. I've mentioned on this slide just a number of the other possibilities. One of the things that is likely to become more and more important as we struggle with the energy efficiency of processors is that the other assumption that you have, that your chips are running at a constant performance, that also is no longer the case. But there are just many, many of these sources of delays, and that means that the assumptions that underlay the bulk synchronous model are really becoming outdated. Okay. So our summary so far, we've got this, I'll say BSP for both the bulk synchronous parallelism and bulk synchronous programming. It does provide an effective way to reason about parallel programs. It addresses, particularly in invariance formulation, the performance and correctness. There's a formal model of performance in there. But unfortunately, it's an increasingly poor fit to real systems, particularly at extreme scale. So what do we need to do? How do we need to think about this? So we really need a more formal way to think about programming, and it has to be based on the realities of real systems. Those of you who might know about the PRAM model, the PRAM model is a model that is useful for proving theorems about the limits of what is possible with a parallel computer, but it doesn't really provide a practical model for designing practical codes. And a very important point, and perhaps one of the most important points I want to make today, is I'm not talking about a programming model when I'm talking about how I think about parallel programming. One of the things I really would like you to take from this is that you need to think about the parallel programming separate from the programming model. So first we need to think about what the system can do. And the system is the hardware and the software together. And I am going to be a little vague about some of these things, but that's, I think, an important part of starting to rethink how you approach parallel programming. So I'd like to ask you to separate the programming model, the way you write your algorithm, from the execution model. So what is an execution model? It's your way of thinking about what the computer can do, not how I would write the code for it, but what the computer does. And why do you talk about that? Well, the execution model can influence what you consider as a possible solution. In linguistics, there's a thing called the Whorfian hypothesis. The strong form of this was discredited, which was that the way you think about everything is based on your language. But what some people might call the weak form, there's a significant amount of evidence for that. For some things, the way you talk about it does influence the way you think about it. And it's really time to go back and start thinking about what the hardware does or could do, what the base system does or could do, separate from the way that we program it. So what are some examples of an execution model? Well, a von Neumann machine is an execution model. You've got the program counter, the arithmetic logic unit, you've got addressable memory. Another example would be a classic vector machine, so like a cray, where you added an object, which you call a vector, which is a group of data on which a single instruction would perform many operations. The CDC star 100 had effectively arbitrary length vectors. They were memory-to-memory operations. Crays used vector registers of size 64. And more recently, the commodity processors have been adding floating point performance by having effective short vectors, 2 words, 4 words, things like that. GPUs, with collections of threads or warps or however you want to describe it, that's another execution model. Okay. A programming model is the way you express an algorithm in a way that can be turned into code. In the beginning, there was a very tight connection between these. So Fortran, which stands for formula translation, was pretty tightly connected to what the von Neumann machine could do. The original C had operators like plus plus that were directly represented by the capabilities of the hardware. There was an increment instruction that would turn into. Now, over time, the hardware has changed quite a bit. So our execution models have changed. The reality of this has changed. But the programming models really have not. And we've tended to rely on the compiler to hide the changes from the user. So you rely on auto-vectorization and so forth. The consequence of this is that there's now a big mismatch between what the user expects and what the system can do. And that often makes it hard to exploit what the system can do because the user is thinking in terms of what the programming model gives you. And for those of you who think that that's okay, that you'd like to have a nice clean model for the user and then somebody else takes care of it, the unfortunate fact is that this is incredibly hard, and decades of compiler research, for example, have shown how hard it is because they have tried and in many ways been unable to fully automate this process. I also want to distinguish here between programming model and system. This is another area that's important to keep straight, particularly in parallel computing. So a programming model, like an execution model, is an abstraction. In the case of a programming model, it's an abstraction of a way to write a program. And it could be, that abstraction can be on many different levels. It could be just whether it's procedural or imperative. It could be down to whether you consider vectors as part of the programming model, the abstraction. And the programming model can often be expressed with pseudocode. I want to distinguish this between what people use in practice. I'm going to use the term programming system, and that's an application programmer interface that implements parts of one or more programming models and allows the precise specification of a program. That's very different than a programming model, and there are very few examples of programming systems that are a pure implementation of a single programming model. So why the distinction? Well, those of you that know MPI, the message passing interface, may have heard it described as a programming model. That's in fact not correct. It's a message passing is a programming model. It's an abstraction that talks about how a program can send messages back and forth. The message passing interface is an API, and it implements multiple of these programming models. It does implement, for example, the bulk synchronous parallelism model. It also implements one-sided communication. There is in MPI-3, there is support for a shared memory programming model. Similarly, CUDA or OpenACC or OpenCL, those are not programming models, they're programming systems. Okay. And the devil here is in the details. So there is no unique execution model. In many ways, you could argue there's no unique programming model. The question as you are thinking about making use of one of these things is, what level of detail do you need to design and implement your program? And again, remember, parallelism, we're after performance. We should be understanding how to make use of the best resources of the machine. Now, if you reach this point and you say, well, I know how to think about things and everything's fine and I'm getting the performance I need, then great. It ain't broke, don't fix it. But if you find that it's starting to become difficult to get the performance you need because of the way you were thinking about the code, this is a great time to step back and start looking for different ways to think about it. So one thing to do is to change the execution model that you use. Now, that's because most programmers are using an execution model that is not an accurate reflection of what the hardware can do. So for example, change to an execution model that no longer makes assumptions of performance regularity. There may be limits to the variability, but perfect predictability is something that you may not have. So make that part of your execution model. Bear in mind that synchronization costs are high and that they will amplify because of this cascading effect. Remember that memory operations are quite costly. Moving memory from DRAM to a register on a typical machine is almost as costly as moving data between machines if you have a very high performance interconnect. So bear that in mind as part of your execution model. And another piece that's often missing is hardware these days have many interesting operations, few of which are directly accessible through our programming systems. And as a designer for an algorithm, start thinking about how you might use those, lobby to get those included in your programming system. So how does this change the way you should be looking at parallel programming? Well, you need to be more dynamic. You need to plan for performance irregularity. Of course, you still need to take advantage of what regularity you can find so that you don't have too much overhead. Recognize that communication takes time, and time which is not predictable. And that's true whether you're talking about communication between memory and cache or elsewhere. Think about the abstraction that you use for this execution model. And then finally, use a programming system that allows you to express the elements that you need from the execution model. Okay, so just quickly to wrap up here, if I go back to that mesh computation and I want to rethink it, well, that was done with the assumption that performance was predictable. So I'll go away from that. One solution there is to now over-decompose the mesh into even more pieces and then dynamically schedule those pieces among, for example, threads on a node to allow them to adapt to various sorts of performance irregularities. For communication delays, I may choose to use different approaches, for example, one-sided communication that has less synchronization in it. I may choose to use more non-blocking communication so as to provide more opportunities for the delays to be squashed. Thinking about, again, these irregularities and how they impact the code. So the takeaway here is be aware of the capabilities of parallel systems, not just what a programming model or a programming system provides. Think about the realities of the execution, and as always, use as simple of an abstraction as you could get away with, but no simpler. And then find a system that will allow you to express your algorithm. And don't be confused by statements that a particular programming system only implements a particular programming model, because this is almost never the case. There are lots of things to look at. I've really only touched on this. I hope that you'll go out and look at other work that's being done in this area. I've listed a few things here because, mostly because I know these people and I'd like you to look at them, but there are, of course, many other things. For example, Charm++ and Adaptive MPI provides a much more dynamic form. There are various thread-based tools. There are research systems. There's one at Delaware called Earth and Earth-Threaded C. There's a number of projects that the Department of Energy is sponsoring that are looking at other programming systems that implement much more dynamic approaches. And one of the fun things here is that there's a great opportunity for algorithms that match more realistic execution models, ones that, for example, don't have those blocking dot products inside a conjugate gradient step. So there are many such things. I encourage you to go look at them. You can search for execution model and parallel computing to find them. And I'll put in a plug to join us all at SC13 this November, where you can talk to about 10, 11,000 other people who are interested in using parallel programming. So let me just, before we do the questions, let me just put up one last question. I'm just sort of curious if how you see the use of parallel programming in HPC changing. Do you think it's going to stay the same or increase or decrease? And let's do this quick, and then we will get to the questions. I'll give you one more half minute here. Okay. Well, that was great to see that almost nobody sees it decreasing, and most people see it increasing. That's sort of what we expected. So, oops. Oh, let's see. I have pushed the wrong. There we go. Okay. So at this point, I think we could take some questions.
Great. Thanks, Bill, for the great talk. We do have lots of questions, way more than we could get to, even if we had another hour. So I do want to mention that Bill is going to tackle some of the questions offline, and the answers will be made available to all of the registrants. So if you've got a question, go ahead and submit it, and we'll get to it offline. But let's pick a couple to address while we're all together here. Bill, there was an interesting question that observes that in nature there are lots of processes, whether, for example, that don't need to complete a global synchronization in order to proceed locally. So do you have any thoughts on lessons we can learn from nature as we go to building larger hardware and software systems in HPC?
Yeah, so that's a great question, and it's nice I can refer to the mesh example. In terms of the communication there, we do have only this sort of local light cone communication. So that means that as one's thinking about expressing the algorithm, you want that execution model that you're thinking about to contain that same concept that that there is no global synchronization, that there is just this need to communicate in your light cone. The harder part has to do with some of the algorithmic issues, but I think that by looking at how nature does it and using that as a way to think about your computation and breaking yourself away from a particular programming model that might introduce extra synchronization. So, for example, as I mentioned, these models where you complete communication globally, even though you may only specify it locally, that's an example of sort of over-specifying things. So, yes, I think if you back up and look at it and look at what the hardware can do, what the execution system can do, and then demand of your programming system that it support that, you'll be able to take advantage of those.
All right, great, thanks. We had several questions around shared memory and sort of how do the things that you were talking about today, which seem to be mostly focused on distributed systems, apply to shared memory systems, and do you see shared memory semantics becoming more important as the number of cores inside a single piece of silicon gets larger?
So I'll take the sort of radical position that in many ways I argue that they're not that different. Shared memory gives you some nice hardware that makes it easy to access other data, but you still have many issues to deal with, and in fact, in many shared memory programs, people do make local copies of data because of the performance impact of not having that local data. And even when they don't do it, the hardware does it because it manages it through the cache system. And similarly, the performance irregularity will also apply to the shared memory system. So yes, the one example that I gave was much more distributed memory, but very much I think in the shared memory case, it's important, again, to think about what the hardware does. For example, a lot of hardware has some very nice instructions for certain types of either atomic updates or guarded accesses, and yet most of our programming systems don't provide good ways to make use of them, and then we get codes that bend over backwards to do stuff that, in fact, the hardware and a programming system that more accurately reflected the execution model might make easy. So again, from a high level, I think that they're pretty similar. And then specifically, it really all comes down, again, to data motion, and whether that data motion is by sending a distributed memory message between nodes, or it's moving data between memory and cache, or between different levels of cache. The reality has been that the programmer needs to be at least a little bit involved in organizing this, at least at the algorithmic level.
Bill, we had a couple questions around domain-specific languages. What role do you see them playing in a parallel programming future?
So I think that they're important. I will say that it's another case where they have a terrible name. So I like to call them something different, and then I think that it clarifies what's going on. I like to call them data structure-specific languages because they're really organized around maybe an abstract data structure. So MATLAB, for example, it's hard for me to define. In fact, I would be scared to try to define the domain that MATLAB applied to. But if I call it a data structure-specific language, well, that's in its name. And these data structure-specific languages, I think, if they are properly integrated into a programming system, will be a tremendous help. And it's because that they will deal with the complexities of handling those data structures in an application. And very much Whorfian hypothesis here, if you think of it as a data structure-specific language, then you realize that part of that integration into a richer environment is going to be how do you move data between different types of data structures. And that's going to be a key part of making DSLs an effective part of the parallel programming solution.
All right. Well, I really appreciate it. We have a record number of participants and an outstanding number of great questions. So as I mentioned earlier, Bill is going to try to get to at least some of those, hopefully all of those offline, and we'll make those available to all of the registered participants. So we appreciate that. So I'd like to once again thank Bill for his presentation. I want to thank all of you for taking time out of your day to participate and submit great questions and comments. We're going to use all of those to make the next experience even better. So we hope you come back to the next ACM webinar and stay engaged with us. We also want to ask you to take just another 30 seconds to fill out the survey by clicking on the URL on the screen, which will help us make the next experience better for the next group of participants. And I want to remind everybody that this webinar will be available on demand in a few days at learning.acm.org. And don't forget to check out ACM's other great learning resources at acm.org and learning.acm.org in the coming weeks for announcements on upcoming webinars and events. So one last thing I want to close with, if you have ideas for future topics for these webinars, please send them to us. The email address is learning@acm.org. So thanks everybody, and that concludes our session today.